Hello, can you hear me?
Yes, sir.
Hello. Okay. In the last class, we have started talking about principal component analysis, and today we will look at the steps of principal component analysis, and we will try to understand how we can maximize the variance along the direction of eigenvectors. Okay. So there are a few steps. Initially, what we do, we consider a given feature vector. Okay, we consider a given feature vector x1 to xm. Okay, and here n is the number of features and m is the number of samples. Okay, so here we are considering m number of samples with n number of features. So in the first step, we will compute the sample mean. So here in the first step, we have to compute the sample mean, and in the second step we will subtract the sample mean. So here we get the deviations between the centroid or the mean uh, and the data point. Okay, so every we get the deviations from mean for every data point xi, and that we have to preserve for computing the sample variance covariance. Okay, so in the third step we compute the sample covariance matrix sigma x. So here sigma x is given by 1 by m summation over this xi minus mean. Okay, and which is multiplied with the transpose of this deviation xi minus x bar. And we can write this covariance matrix in the in another form, so which is given by 1 by m this summation over this phi I and transpose of phi I. And we can say that here a is given by a vector of m number of deviations. Okay, m number of deviations. So here the column of a are phi I. So here we get m by n by m matrix, where n represent the number of features and m represent number of samples. And in the next step, we compute the eigenvalues and eigenvectors. So we get this relation sigma x ui equals to lambda I ui. So this sigma x is the covariance matrix, ui is the unit vector, and lambda I represent the eigenvalues. Okay, and if we take the right hand side on the left hand side, then we will get the sigma this sigma minus lambda I into ui equals to 0. So here we assume that lambda 1 greater than lambda 2, and lambda n minus 1 will be found to be greater than lambda n. So we can arrange these eigenvalues according to the order of the features. Okay, so if we have n number of features, then we can get the arrangement of the eigenvalues like this. Now here sigma x is found to be symmetric, so we can form an orthogonal basis in n-dimensional feature space, and we can represent any feature vector which is found in n-dimensional feature space as x minus x bar. Okay, x minus x bar, which is given by this summation over yi ui. Okay, linear combination of yi ui, and yi here yi is given by the transpose of deviation, that is x minus x bar into ui, and in the denominator we will get the transpose of ui into ui. Okay, now if the norm of ui is found to be 1, then we will get the transpose of these deviations, which is multiplied with ui. So what we are doing here, we are transforming the basis. Okay, That means we are changing the basis from this x minus x bar. So x bar, so this is actually represented in terms of yi. Okay, so here yi, here I varies from 1 to n. For n number of features or n number of attributes, we are getting this linear combination of yi and ui. Now when we compute the principal components in terms of eigenvectors and eigenvalues, so you have to remember this relation sigma x ui given by lambda ui. Now to reduce the dimension of the given feature vector, we have to approximate the given feature vector x using only the first k eigenvectors, where k is found to be very less than n. So that means the corresponding this will be the corresponding to the k largest eigenvalues, where k is a parameter. Okay, so we have to provide this value k. So there is no thumb rule for determining the value of k, but we can estimate the k in different way. But here, if we assume that the value of k is estimated, then k should be less than n, and we will get the first k eigenvectors corresponding to the k largest eigenvalues. And these k largest eigenvalues represent the distance from origin, and here we get the actually get the distance of the eigenvectors along the axis that we have determined for principal components. So what we do, we actually get this linear combination of yi and ui in terms of x, and then this given feature vector is to be approximated. And when we get the approximated feature vector, after having selecting the first k eigenvectors, then this can be represented by x cap. Okay, so this x cap denotes the approximation of x. So using the first k eigenvectors, we can approximate the given feature vector. And if we get a linear combination over k number of eigenvectors, then we will get the linear combination of yi and ui. Okay, and this is what we call the reconstruction. This is what we call the reconstruction. So initially, what we obtained, we obtain a transformation from here n number of features to n number of features for the given feature vector to uh, n number of features of transformed y features. Okay, and from there we can get the approximation over the given feature vector x over for first k number of eigenvectors. So when we arrange the eigenvalues in descending order, then from there we can select a subset of k number of eigenvalues, and k number of eigenvalues with their corresponding k number of eigenvectors will give us this approximation. Now, when k is found to be n, okay, that means when we get the zero reconstruction error, so in that case, the approximation of x should be equal to x itself. Okay, that means in that case, the approximation will be found to be same as that of the given feature vector x when k is found to be n. Now here, when we compute the covariance matrix sigma x, so this sigma x, as I said, that we can represent the covariance matrix in terms of the deviations between each feature point and centroid or mean. And here we get the deviation and transpose of that deviation, over which we get this summation for m number of samples. Now, in principal component analysis, we choose the eigenvectors of the covariance matrix corresponding to largest eigenvalues. Okay. So here, if we look at this graph, then here we can see there are two principal components are determined, u1 and u2. Okay, and these two principal components are determined over this distribution for two-dimensional data x1 and x2. Now, PCA in principal component analysis. So here we choose the eigenvectors of covariance matrix corresponding to largest eigenvalues. Or we can say in other way we can say that we can maximize the variance along the principal components which corresponding to the eigenvectors. Okay, so the eigenvalues correspond to the variance of the data along the eigenvector direction. So in the direction of eigenvectors, so we get the variance to be maximized, and this will give us the principal components which is corresponding to the eigenvalues. So here principal component analysis projects the data along the directions where the data varies most. So as I said in the last class that when we get the distribution of n-dimensional data, so n may be 1, n may be 2, n may be 3, or n may be more than 3 dimensional data. So first we get the distribution of the data points in the xy coordinate or plane, and accordingly we will get the centroid value, and then we are shifting the centroid value to the origin of this coordinate, and then we will project the data points along the direction of the straight line that we are getting. So this straight line is nothing but the best fit line, and sometimes this lines is found along the direction of the eigenvectors or along the direction of the principal component where the data varies most. Okay, so in this direction, if we consider a particular direction along u1, then here you can here we can see that and along this direction we can see that data varies most. Okay, so most of the data are found to be uh, varies along this direction u1. But if we consider the u2 direction, then in this direction we also get another principal component, that is principal component 2, but in along this direction we do not get the data which varies most. Okay, so either we can consider both the principal components for further computation, but if we consider the principal component 1 along u1 direction, so this will be justified to get the data to be varied most. Now, principal component analysis preserves as much as information in the data by preserving as much variation in the data. Okay, so another objective of principal component analysis is to preserve as much information in the data by preserving the variance in the data. Variance means the if we get the maximum when we get the maximum variance along a certain principal component analysis along the direction of the certain principal component analysis, so we will look into it, and we will get that principal component for further computations. Now we will take an example, and we will compute the eigenvalue and eigenvectors. Now here we have been given a 3 by 3 feature vector. So this feature vector is denoted by capital C. So C is given by this 3 by 3 feature vector. Now if you remember the equation that a minus a minus k, and this is the KUI. Okay, so if we consider this is a minus ki equals to 0. Okay, so a is nothing but the given feature vector, and k here represent the eigenvalues. Okay, now this eigenvalues is multiplied with the identity matrix. Okay, identity matrix, and here we get the determinant of this matrix. Okay, 3 by 3 matrix. And after solving this determinant, so here we will get three values for k. That means three there are three eigenvectors, so that are corresponding to these three eigenvalues. Okay, so since here k represent the eigenvalues, so therefore here we are getting three eigenvalues and three corresponding eigenvectors that we have to compute. So first we compute the eigenvalues, then we will compute the eigenvectors. Now to compute the eigenvectors, we will use the same equation, but at this time we get a minus ki into this v, and this v represent the eigenvector. Okay, since it is a three-dimensional data, so therefore in the v we will get x comma y comma z. Okay, for three-dimensional data, we are actually getting three eigenvalues and corresponding three eigenvectors. Okay, so to compute the eigenvector, we will consider the same equation. Now this a minus ki will be multiplied with this eigenvector v, and this will make 0. So we will make this 0, and here k represent the eigenvalue. Now we will substitute the eigenvalue in the in this equation, and we will solve this linear equation to find the value of k. So if you are familiar with the if you are familiar with the numerical analysis, so you can solve this linear system of equations uh, for eigenvector. Okay, so here after putting these eigenvalues in this equation, so here so one by one we will consider the eigenvalues and get the corresponding eigenvector. So first we will write the given feature vector. Okay, 3 by 3 this matrix, and then we will get the eigenvalues in place of k, and then we will write the identity matrix. Okay, and this whole thing will be multiplied with this one dimensional vector, so x y z. Okay, so here we are taking we are taking the transpose of this xyz, and we are multiplying with this equation. Now we have to solve this linear system of equations, and when we get it solved, then after solving we will get x equals to 2, y equals to 1, and z equals to -1. And similar to the first eigenvalue, we will get two other eigenvalues, 3 and 6. Okay, 3 and 6, and accordingly we will get the eigenvectors corresponding eigenvectors for another two eigenvalues. And after solving the linear system of equations, then we will get uh, uh, two sets of values for x, y, and z. Okay, now here we have to do we have to do one more task, which is we have to arrange these eigenvalues in descending order. Okay, so if we arrange the eigenvalues in descending order, then we will get 6 first. Okay, then 3 will come next, and finally we will get -5, and accordingly we will get the eigenvectors as principal component 1, principal component 2, and principal component 3. Since this is a three dimensional feature vector, so therefore you will get three eigenvalues and three eigenvectors. So after having the eigenvalues and eigenvectors, we will arrange these eigenvalues in descending order, and we will get the largest eigenvalue in the first position, then we will get the second largest eigenvalue in the next position, and finally we will get -5. and accordingly we will arrange the corresponding eigenvectors for getting the principal component 1, 2 and 3. So among these three principal components, we can, if we want to preserve all the uh, mm, preserve all the eigenvectors, then we can consider all the principal component analysis, all the principal components. Or in other way, we can get the approximation by considering a subset of eigenvectors. Okay, a subset of principal component. That means out of three, we can consider two. Okay, so if we see that this two principal component gives 90% of the variance along this along principal component 1 and principal component 2 direction, then we will obviously going for choosing the first two principal components. If the first two principal components or first two eigenvectors give 90% of variability, then we will going to consider the first two principal components. Otherwise, we can consider a k equals to n, where the number of eigenvectors or number of principal components will be found to be same as that the number of features. This is another example. So here we have considered a data set. So here we have considered a data set of two-dimensional data. Okay. So here we are having 1, 2, 3, 4, 5, 6, 7, 8. Okay. So here we are having 8 samples of two-dimensional features. Okay. So here we can compute the covariance matrix. Okay, so here we get the covariance matrix. So in the previous example, what we have done, we directly put the feature vector in this determinant. Okay, so a minus ki we are considering here. But in the next example, what we are doing, we are computing the sample covariance matrix. Okay, so here we are getting the sample covariance matrix, and then we get the eigenvalues, which can be computed by finding the roots of this characteristic polynomial. Okay, this is nothing but the uh, solution of, we have linear system of equations. Okay, solutions of linear system of equations. So when you get the linear system of equations, so when we get it solved, then we will get the eigenvalues here, lambda 1 and lambda 2. Since we have considered two-dimensional feature vector, therefore there will be two eigenvalues and corresponding to eigenvectors. So first we are computing the eigenvalues, then we will compute the eigenvectors. Okay, now the question is how to choose k. Okay, so how to choose k? So if we have more than, let's say, 10 dimensional data, or 20 number of features are present in the given data set, then out of 20, so how we choose the k? That means the k number of eigenvalues or k number of eigenvectors. So how can we choose this k? Okay, now K is typically chosen based on how much information we want to preserve. So that means if if we can represent the maximum variance with K number of eigenvectors, then we will choose a subset of n number of subset of n. Okay, and this subset of n can be represented by this k. That means if we get maximum variance along k number of principal components or along k number of eigenvectors, then we will go for this k number of eigenvectors. Otherwise, we can choose the n number of eigenvectors. That means all of the eigenvectors, all of principal components we can choose. But this will not give us the reduced dimension, since we are our principal objective is to get the reduced set of features. So therefore, we have to choose the k carefully so that we can get the maximum variance along those k number of principal components. Now, how to set a criteria based on which we can choose the k. Okay. Now we can choose the smallest k that satisfies this inequality. Okay. Now let us consider we are getting this lambda value for k number of features, and here we are getting lambda value for n number of features. Okay, that means here we are considering the eigenvalues for n number of features, and in the in other hand we are considering this lambda value or the eigenvalue for k number of features. Now we will take the ratio of these two. Okay, we will take the ratio of these two, and then compare we will compare it with the ratio will be compared with the threshold. Now if we set a threshold value 0.9, then when this inequality will be satisfied by this k value, that means we will choose that k number of eigenvectors and eigenvalues. Okay, otherwise if it does not satisfy this inequality, then we will change the k value, and then we will again try whether this ratio is found to be greater than t or not. So when it is found to be when it is found to be greater than t by changing the value of k, then we will stick to that number k, and we will get the corresponding number of eigenvalues and eigenvectors. So this is one criteria based on which we can select the k number of eigenvalues and k number of eigenvectors. So here if you set the threshold value is 0.9, so what does this mean? This means that we can preserve 90% of the information in the data, because here we are getting the ratio between this summation over sigma lambda I and this summation over lambda I for k number of features and for n number of features. Okay. Now, if we write t equals to 0.8, that means we can preserve 80% of the variance in the data. Okay. So we have to set we have to set as much as percentage, so that we can preserve the more information as variance in the data. Okay, now if k is found to be n, that means we will preserve 100%. In that case e will be found to be 1. Okay, will be found to be 1. So we can vary the threshold value, let's say from 0.95. Okay, so for the first time we will get 0.95, for the second time we will get 0.9, and then we will try to vary the value of this threshold, and accordingly we will get the ratio to be satisfied this inequality. Okay. Now this approximation error or the reconstruction error, so this can be computed by norm of this deviation. Okay, so we get the approximation, and then we get it deducted, subtracted from the given feature vector x. Okay, and by this way we can get this reconstruction error. So as I said, that when k is found to be equal to n, so the reconstruction error will be found to be 0. Otherwise, for approximation, we will get some reconstruction error or approximation error. So here in this norm of this deviation, the approximation is given by this summation over yi and ui. Okay, plus this x. Okay, so this is nothing but the reconstruction. So this x bar represent the this x bar represent the reconstruction. So here we get the approximation. So if we get this x bar on the other side, then this will be given by summation over yi and ui for k number of features or k number of eigenvalues. So the approximation error that we have computed has norm of deviation between x and approximation of x. So this norm can be given by half of the summation over lambda I. Okay, half of summation over lambda I. So this summation is computed for I equals to k plus 1 to n, okay, over this lambda I. So here lambda I represent the ith eigenvalue. Okay. Now here we can get the application of principal component analysis to images. So let us consider here we have been provided the m number of images of n by n dimension. Okay, m number of images of n by n dimension. Now first we represent each image as one dimensional vector by stacking the rows together. Okay, so here we get this n by n image as this one dimensional feature vector. Okay, so here we get the rows to be stacked together. And in the next step, we will compute the covariance matrix. Okay, next step we will compute the covariance matrix. Now, if we see, and then we will compute this A transpose or A transpose which is multiplied with A. Okay, so what is A transpose? So here A transpose. So here the A transpose is so this we will get the eigenvalues and eigenvectors of the. So this is the given feature vector. So if we get the given feature vector as okay, so here we get the given feature vector which is multiplied with ui, and this is given by lambda ui. Okay, so here we get this covariance matrix. So in the covariance matrix we get these features to be encoded. So the encoded means this phi I and transpose of phi I actually represent the matrix n square by m. Okay, n square by m. So this phi I is nothing but the deviations between centroid and each feature point. And if we get the summation over this phi I and transpose of phi I, we will get this covariance matrix. And in other way, we can write the covariance matrix which is given by 1 by m into into a transpose. Okay, so now this a and a transpose is multiplied with the unit basis vector or unit vector which is given by this lambda I and ui. So first of all, we need to compute the A transpose A and this multiplication A. And in the next step, we will compute the mean and variance of this A transpose. So we will get a matrix if we multiply multiply the transpose of A and A, and here we compute the mean and variance from this matrix. And in the next step we will compute the lambda I. So we will compute the eigenvalues, okay, and corresponding eigenvectors. And then in the dimensionality reduction we have to approximate x using only the first k eigenvector. So that we have computed how we can choose the k values by taking the ratio and selecting the corresponding k eigenvector. So we have already gone through this. Okay. So here is the data set. So for each face image, you will get a two-dimensional matrix. So we will have the arrangement of this two-dimensional matrix. So here you can say that there are 10 samples. Okay, so there are 10 samples for each class. So since it is the unsupervised learning algorithm, therefore this PCA is responsible to discover the patterns along the principal components or along the eigenvectors. Okay, so whenever we see the maximum variance along a certain number of principal components, so we will get the principal component, and we will make a reduced feature set. Here you can see the mean face. So these are the mean faces. Okay. Now, what are the limitations of principal component analysis? So, principal component analysis is not always an optimal dimensionality reduction technique for classification purposes. Okay. So, this is one of the most prominent limitations of principal component analysis. Now, to get rid of this problem, or we can get the problem in different way, so we can consider another we can consider another dimensionality reduction technique, which is known as linear discriminant analysis. Now as we know that principal component analysis maximize the variance along principal components, but when we consider linear discriminant analysis, so linear discriminant analysis maximize the separability between between different classes. Okay. Now what we get in linear discriminant analysis. So the goal of the linear discriminant analysis is to find the directions along which the classes are best separated. That means along these directions we get the maximum separability between the classes. Okay, that means we are increasing the discriminatory information. So we have to increase the discriminatory information so that we can best represent the classes with maximum separability. Now it takes into consideration the scatter scatter matrix, that means the variance within classes and between classes. So at the same time, so what we do, we consider two different two different aspects. One is the within class scatter matrix and between class scatter matrix. That means within class variance and between class variance. Okay, let us consider there are two-dimensional data. X1, so here X1 represented along x-axis and X2 represented along y-axis, and we get the data points to be plotted in this XY coordinate. Okay, now to get the projection of these data points on a line, if we consider a straight line. Okay, let us consider a straight line as a basis, and on which we project these data points, and here we get the projection direction. Okay, this is the projection direction, and this projection direction is determined along this straight line. Okay, and we are projecting these data points onto this line. Now if we consider such separability, and this and here after projecting the points onto this line, we will get two different means, since there are since here we are considering two-dimensional data, and if we here we are considering two classes. One is the red class. Okay, so here you can see that some points are marked in red class and rest of the points are marked in blue colors. Okay, so here we are having two classes. Okay, for two-dimensional data, and after projecting these points on the line, we have to compute the two means, one for the blue class, another for red class. Okay, and then we will get the scatter for red class, scatter for blue class, blue color points. Okay, then we will compute the ratio between the deviations between means. Okay, so we will take the square of these deviations between mean in the numerator. In the denominator we will get the square of the variances or square of the scatters, and then we get the summation. Okay, and if we take this ratio, then we can get we can get the separability to some extent, but this is found to be the bad separability. Okay, if we consider a line over which we get the projection of the data points, then and after that we will get the ratio between the deviations of means and the summation of scatter matrix, then we will get the bad separability. Okay, now, if we consider these points, that means here in the first case, when we get the bad separability, so in this case, we are not considering the two aspects. The two aspect means within class separability, okay, and between class separability. That means the variance that we are considering within class and between class, so they are not considered over this over the first case. But if we consider for the good separability, so here we have to consider these two aspects: within class scatter matrix and between class scatter matrix, and these two aspects will be considered at the same time to get the good separability. Now let us consider there are C number of classes with each class containing A minus number of samples. Okay, A minus number of samples. So here I can vary from 1 to 1 to C number of classes, and M is the total number of samples. Okay, so here we get the mean. So mean, first we will get the mean for a particular class out of C number of classes. Okay, so for that means if we are having C number of classes, for C number of classes you will get this mean. Okay, you will get this mean, and here mu is the mean. So mean for each and every class, and here we will get another mean. So this mean actually represent the mean of the whole data set. Okay, mean of the whole data set. Now what we are doing, we are getting the within class scatter matrix, and if the within class scatter matrix is represented by this SW, then this SW is given by this double summation over x tj minus mu j, and this will be multiplied with the transpose of these deviations. That means this double summation is computed over these deviations and transpose of deviations for C number of classes and mi number of samples. Okay, and then we will get the between class scatter matrix. So between class scatter matrix is computed as the deviations, as the multiplications of deviations between the mu I, which mu I for each class, and the global mean means this global mean is computed on the whole data set. Okay, so we are taking this mu I minus mu transpose of mu I minus mu, over which we get this summation for C number of classes, and this will give us the between class scatter matrix. Now suppose the projection transformation is given by y equals to ut x. Okay, this is the projection transformation. So for good separability, we see that so the good separability, what we saw that this these two sets of points, okay, corresponding to two different classes, are found to be well separated. Okay, but for the first For the first case we get the bad separability, but that means the feature points that we have projected onto this line are found to be overlapping. That means they are not separated well. But for the second case we get these two classes are found to be separated well. Okay, now to consider the good separability. So we can get the projection transformation, which is given by y equals to utx. Okay, and in the next consideration, we will consider the matrices of the projected data. That means the after projecting the data onto the line. Okay, so we will get the scatter matrices. So scatter matrix for between class, scatter matrix for within class. Now this LDA is required the transformations so that will maximize the between class scatter matrix and minimize the within class scatter matrix. That means if we are considering a number of instances in the same class, then that means the the transformations that will be generated, so will maximize the within class minimize the within class scatter matrix. Okay, and if we get the instances of obtained from two different classes, then in that case we will maximize the between class scatter matrix. Okay, that means here we are getting the ratio between class scatter matrix and within class scatter matrix, uh, which we have to maximize. So that means we are maximizing this ratio. Okay, and in other way, if we represent the same phenomena, then we can maximize this transformation. Okay, the projection transformation. So we are maximize the ratio between class projection transformation and within class projection transformation. So both will work. We can consider either this or this. So here we can show that the columns of the matrix U are the eigenvectors. Okay, columns of the matrix U are the eigenvectors, which are also called the Fisher spaces, and they are corresponding to the largest eigenvalues of the following generalized problem. Okay, so here we get the between class scatter matrix, which is multiplied with the unit vector uk, which is given by the this lambda k represent the eigenvalue, which is multiplied with the within class scatter matrix. Again it is multiplied with the unit vector. Okay, so from this relation we can compute the eigenvalues and the corresponding criteria based on which we can classify the samples. That means the objective of linear discriminant analysis is to maximize the separability between classes. Now, if a data set is given, so from that data set, so we can have the information about class levels. That means if we have information about class level, that means the linear discriminant analysis is found to be supervised learning technique. Okay, and in supervised learning, since it is a supervised learning technique, therefore the class information or class levels will be provided with the given dataset. And if we have new samples to be recognized or to be classified as a class level, that means that sample, newly found sample, or the samples which have not been classified yet, so that will infer some class levels in the given data set. Okay, so our task is to determine the class level for that new samples using linear discriminant analysis. So using linear discriminant analysis, we can set a criteria, and based on which we can get the classification. We can get the class levels for the new samples by maximizing the class separability between different class levels or different class different groups of classes. If you have any questions, you can ask me. Otherwise, we will stop now. And today I will send you the syllabus of the mid-sem examination. So, and I will also send you this PPT to your mail ID. So you get it from there. And if you have any questions, then you can ask me about mid-semester exam. So until today's coverage, the mid-sem syllabus will be there. Okay, that's all for today.